If we go back to our unit circle, which we met in video 1 of this series, don't forget unit circle meaning radius of 1. And we look at that triangle we created with that base angle x, and of course we had then the height of that triangle was sine x, and the base of that triangle was cos x. We're going to explore this a little bit more to try and give ourselves some identities which will help us solve equations with trig in a little bit more detail. So this triangle, it's a right angle triangle, and one of the identities is something that we've already looked at previously. So we know from our GCSE trig ratios that tan of an angle is the opposite divided by the adjacent, in which case we know that tan of x is the opposite, sine x, divided by cos x, the adjacent. And that's an identity that we can use if we see a relationship in a question. We leave it as a single equals though, we don't put it in as an identity, and that's because there are some values of x where this doesn't work, and that's where the asymptote lines appeared in your tan graph. So they were pi by 2, 3 pi by 2, 5 pi by 2, they were minus pi by 2, minus 3 pi by 2, and so on and so forth. Essentially the odd multiples of pi by 2. So we could say where x cannot equal the odd multiples of pi by 2. So 2k minus 1 being a way of representing an odd number, and we're just saying there that k is an integer. That's a lot of fancy language. You don't actually need that second bit. The bit really that you're going to need and use the most is the left hand side of that box. But if you want the fancy stuff, the reason we leave it as an equal sign rather than a triple equals, so an identity, is because there are some values of x where it doesn't work, and those are the values where we get the asymptotes, and we get the asymptotes, or rather the function starts behaving in that way, behaving asymptotically, because cos is getting closer and closer and closer to 0. At the points where cos is 0, so the odd multiples of pi by 2, we have a problem. Tan is undefined there. The other identity comes from the fact that because this is a right angle triangle, Pythagoras holds. And so this is called a Pythagorean trig identity. You'll meet some more later in your course, but Pythagorean trig identity. So we know that the sum of the short sides squared equals the hypotenuse squared. So that's sine of x squared and cos of x squared, and that equals 1. Now, a couple of things to say about this one. Number one, that notation is fine, it does what it needs to do, but as you can imagine, everyone gets very sick and tired of writing the brackets. So in order to get rid of the brackets but not end up looking like we want sine of x squared, we write sine squared x, and that really notation wise just means that that's sine x all squared, but that's how we write it. Obviously we can do the same for cos. So when you see this formula in textbooks and online, you'll see it sine squared x, cos squared x means the same thing. And no matter what value of x we make this function, so no matter where we put this triangle on our unit circle or how many times around we go, we are always going to end up with a right angle triangle, and this will always hold. And because it works for all values of x, we know that it's a full identity. So we can leave it, write it with a triple equals sign. So these two, if you're following the A-level course, particularly the Pearson Edexcel one, these aren't in the formula book for you, so you do need to know them, but by the time you get to your exams, I suspect you're going to know these ones pretty well. So let's have a look at how they apply, and I've put them up in the top right hand corner there just because they're new for us. So if we have a look at this first equation here, we've got a bit of a problem, and the problem is that I've got mixed trig functions within my equation. I've got coses and sines, and that's a bit of an issue if we're trying to apply any of the ideas that we've done previously with questions, or in fact apply anything new really. So one of the things that I can do is use the Pythagorean identity to replace the cos squared with, and I just need to rearrange this, so cos squared x is 1 minus sine squared x. And that's nice because now I have an expression just in terms of sine completely. Now, don't notice that Pythagorean identity has squares in it. So I can't do that with the sine expression. It has to be a squared. So the cos squared would be the one I'd change. So cos squared has changed to 1 minus sine squared x, and the rest of my equation stays the same. I'm just going to simplify this through. So minus sine squared x minus sine x plus 2. I think multiply by a minus 1 as well. And now, looking at that structure, I'm hoping you can see something. I'm hoping you can recognise it to be something. It looks awfully like a quadratic. So if I let y equal sine x, and we work from right to left, obviously the 0 doesn't change, neither does the minus 2. And then I end up with sine x, which is y, and then sine x all squared, which would be y squared. That should be fairly nice to solve. If I can do factorising. Y equals minus 2 and y equals 1, so sine x is minus 2 and sine x is 1. Now, the first expression here is asking, where does sine x equal minus 2? If we have a look at a sine graph, it goes from a maximum of 1 to a minimum of minus 1, and we're saying, where does it cross the line minus 2? Well, it doesn't. So you would actually need to explicitly say no solutions there. You shouldn't just leave it alone. Say mathematical error, whatever you like, but actually acknowledge the fact that there aren't any solutions to be had for that first expression. And for the second one, we're asking, where does the function cross its maximum point? The first solution where that happens is pi by 2, we can see it. The second solution would be 2.5, so 5 pi by 2, and it would depend on our interval as to which solutions we would want. So we'd want x equals arc sine 1, x equals pi by 2, and if our range, for instance, was 0 to 2 pi, I would stop there. If it was 0 to 4 pi, I would find more solutions, so on and so forth. A type of equation that uses the other identity for us, so the tan expression, what tan is equal to, is something a little bit like this one. So we've just got to be a bit careful when we're dividing by expressions, especially trig. We should always look to factorise first, but in this case I think we're going to be okay. I don't have any squares, so I can't use the Pythagorean identity one. It doesn't work without the squares in it, but I could rewrite this expression to be sine x equals 4 cos x, and then divide both sides by cos. I can do that because I'm not cancelling out cos, which would lose me solutions, but I'm rewriting my expression in a legitimate way. So sine x divided by cos x equaling 4. And we know, of course, that sine x over cos x is tan. So tan x equals 4. Again, depending on the interval, let's just say, for example, that it's 0 to 2 pi. We're asking, where does the function tan x cross with the line y equals 4. Now don't forget, tan goes off to positive and negative infinity, so actually we could just chuck the line in somewhere, not randomly, but sensibly. We know it goes on forever, we don't have the same limitations, and so we're going to find our value, our initial value, by doing arctan of 4. That's going to be there, and we're going to get a second solution by adding pi. So that first solution, don't forget to make sure your calculator is in radians, would be 1.33, and then we're going to add pi for our second solution. So 4.47. So hopefully you can see that actually if you can identify the problem, there are mixed trig functions, normally being the biggest issue. You know that you've now got 2 equations at your disposal to be able to try and help you get your expression into one trig equation, one trig function. So that might be, if there are no squares, try and get into tan. And if there are squares, try and create some kind of hidden quadratic by using a rearrangement of that Pythagorean identity.